Hi guys, so today we're going to start a new chapter. So that will be chapter 13 in your textbook. And we'll talk about transfer of heat. So remember, heat is energy in motion, energy in transfer or in transit. And heat always goes from a hot reservoir to a cool reservoir. Now you have three ways for heat to travel from hot to cool. You have radiation, conduction, and convection. So today we're gonna focus on convection. So that happens with a fluid like water or gas, and there will be no mass. So it's conceptual. So chapter 14 in your textbook. So for example, here you have an igloo. So the picture comes from your book, and you see that um, this is about conduction because ice and snow are bad conductor. So the heat can stay inside and doesn't easily flow from inside to outside. So today we're going to focus on convection, and that happens when you have a fluid, okay, moving again because you have a hot reservoir and a cool reservoir. So for example, in that case, you have a convection cell because the water here gets warmer, so the density will decrease, so it will become more buoyant than the surrounding. So it's like it's gonna float, right? It's gonna rise. So it's very much like you have a balloon inflated with air. You try to push it inside the water, it's going to come up. Okay. It doesn't want to sink because its density is smaller. Okay. So here you have a lower density. So the warmer water will rise. Okay. Then here it will cool down because here the surrounding air will be like a cool reservoir. So then the density it's going to increase and it will sink again, especially because here you have a low pressure area. Okay, so it will be cooled in this area and the process starts again. So you need also a difference in pressure for the convection cells to take place, right? So that will be low pressure, high pressure, so the fluid can move. So here you have like candle, so it will warm up the air. The hot air always rise, but it will go vertically upward. So it means if you bring your hands here on the side, it's not going to burn, right? Because the heat is going in this direction. So let's see about pressure. Pressure always goes from high pressure to low pressure. So for example, if you are in an airplane, inside the body, the pressure is that the atmospheric pressure that you have on the ground. So you have a high pressure, but in the airplane, the pressure is going down. Okay, it's going to be lower. So that's why the ears will pop and can be painful. Okay, so here is the same example, but with air. So if you have a heater here, it has to be close to the ground. The air will warm up, so the molecules will spread out more, so the density will decrease. Okay, so it's going to be buoyant. Okay, it's going to be pushed by the cold air on the side here, like a balloon that you try to push inside the water. So it's going to rise here, right? And then it's going to cool down. And then the density is going to increase again. So it will sink and it's going to be cooled in this area here of low density. So high density, low density, high pressure, low pressure. So you have a convection cell. Okay, so the motion is said to be convective. Okay, it's a convective motion. So that comes from your book, the same idea. So these are the hot water heater here. So you have water going through and it's very hot. And then the air warm up again, it's going to rise and then it will sink again. And you have a convection cell. Now you don't want to have a heater on close to the ceiling, of course, because otherwise it's not going to work. So that's why in dormitories, sometimes students, they have like beds on top of each other. So the higher bed will be the warmer, right? It will be the warmer area of the room. So in the fridge, it's the opposite. Okay, so you have a cooling coil here. Okay, so it will cool down the air. So the density will increase. So it will sink. And then it will bring the heat up. Okay, because it will catch all the thermal energy inside the fridge. So the air will warm up. So it will rise. And then it will cool down again. Okay. So you don't want the cooling coil at the bottom. So here's another example from your book. We talked about how dirt or ground can warm up very quickly relative to the water, for example. It has a smaller specific heat capacity. So when it's sunny outside, it's warm outside, the ground will get warm very quickly. It depends on the type of ground, of course. And you have this upward motion. So these are called thermals or updraft. Okay, so the air will rise. So gliders, they can take advantage of that to go up. And birds, they do the same thing, like hawks. So now usually the ground is warm and the top here is cool. So which is good because if you have a very polluted city like Los Angeles, LA in California, with a lot of pollutant, so if it's hot here and cool there, all the pollutant can be evacuated, right? So it could rise and clean up the city. But sometimes you have a phenomenon called inversion where you have the opposite. So you have cool air here and warm air there. And of course, the pollutants here are going to be trapped. And that's when you have a smoke. So this is not very healthy, of course, because heat cannot go from warm to cool unless you force it. So you need to put energy in. Otherwise, heat wants to go always from warm or hot reservoir to a cool reservoir. Okay, so that's also an example from your book. Here's another example here. So sometimes the convection cells, are not happening. So you want them to happen. You want to make a convection cell to take the heat out, for example, of a computer or of your car. So in that case, you need to use what is called forced convection. So you need to use some mechanical energy. So in that case, you have a fan. Okay, so the fan will spin, pushing the air in this direction. So here you're going to have high pressure and low pressure. So you are forcing the cool air to flow from high pressure to low pressure. So you are making those convection cells. So then it will cool down the motor, right? So cool air here, all that air will pick up the heat, the thermal energy from the engine, and it will leave the engine. Okay? But for that, you need to force the convection cells. You force it to happen. Because otherwise, air wants to go from hot to cool and not from cool to hot unless you force it. So you have to introduce some mechanical energy. So you find that in the car. So in that case, you are using some kind of fluid. You find that in computers, for example, especially as computer get more compact, so it's gonna heat up quicker. So you really need a way to get rid of all that heat. Okay, so you need a fan. Okay, so that comes from the book Conceptual Physics by Paul Hewitt. And if you live by the ocean during the day, you're gonna have the wind blowing, so you have a breeze coming from the ocean. Why? Because you remember water has a specific heat capacity larger than the ground. So it takes a lot of time for water to heat up, right? So the ground here could be at 70 Fahrenheit. Here it could be at 65 Fahrenheit. So here it will be cool and here it will be hot, right? So hot air will rise from the ground and then it will sink again. Okay, so here you have high pressure because the air is pushing, and here you have low pressure because the air is rising. So high pressure, low pressure, and the hot air is going upward. Here you have the opposite at night. Night you have a breeze um, from the ground, right, to the sea. Okay, because it takes a long time for water to cool down because it can contain all that thermal energy, the ground will cool down quicker, right? So the hot air will rise from here and then it will sink again. So the air will go from high pressure to low pressure, and that's how you have a wind, a breeze from the ground. Okay, so that's also some kind of parenthesis. So I recommend to read the chapter from this book. It's called Physics Behind the Headlines, or Physics for Future Presidents. That will be a textbook. Physics Behind the Headline is for everyone. And there is this very nice chapter. So if you have a heat engine, like the first steam engines that you had in the 19th century, during the Industrial Revolution. So that's when thermodynamics was developed, at the time of James Joule, the experiment that he did. He was able to show that thermal energy is a form of energy. So you can go from thermal energy to mechanical energy, or you can go from mechanical energy to thermal energy, right? So with that understanding, you see here you have some kind of fluid. You have your hot reservoir and you have your cool reservoir. So heat goes from hot to cool. Okay, so it's going to flow. Larger is the difference in temperature, more flow you're going to get. Okay, and that will create the motion here. So you get a work out. Okay, so that will be the fluid moving from a hot reservoir to a cool reservoir, and you can produce work. So those kind of machine are called steam machine, and they are never 100% efficient. That's part of the thermodynamics law. Okay. That's also behind the idea of a heat engine that you have in your car. You see here, you have a spark plug. You're going to create heat here. The cool reservoir is outside. This is a hot reservoir. So air will push the piston here that will move the car. So this is how the first steam engines were developed at the time, and they were trying to make them as efficient as possible. So you need a hot reservoir, a cool reservoir, and you can use this process to do work. Okay, so to get some mechanical work. Okay, so Jules was doing the opposite. You have mechanical work, okay, that will turn into thermal energy. So here you use the fact that heat always goes from hot to cold. So that's an interesting story here. I think that this car, it's called the Beetle. It was developed during World War II by the German, by the Nazi, I think. And these cars were really efficient because they had a very high reservoir inside, when they were burning fuel. So it was very hot relative to the outside, which is the cool reservoir. So they were able to have a lot of power. Unfortunately, they also produce a lot of carbon monoxide because the combustion was never complete, right? You have more carbon monoxide than carbon dioxide, so then they stopped producing it. So anyway, okay, so here you have the heat engine principle, and you see that heat, as I've said several times, always flow from a hot reservoir. So that could be called, for example, a source to a cold reservoir, which is called the sink. And this way you can harvest mechanical work. And in the 19th century, many scientists or engineers worked to make those machines as efficient as possible. So the second law of thermodynamics says that heat goes from hot to cold. And then another principle says that you cannot break even. You are always losing energy. Okay, it's never 100% efficient. So here you have like a drawing. I think this one comes from the conceptual physics textbook from Paul Hewitt. So you see you have a turbine here, and that can produce electricity when it's going to spin. So, but the idea is the same, right? So here you have a boiler. So that will be your source. So hot reservoir. So the water will turn into vapor. So with a very high pressure. So that will be a very high pressure steam. So that's here you're gonna have high pressure. And then here you have a condenser. So here the water will be cooler, maybe because it's in contact with water that can be pulled from a river, for example. So this is cool and this is hot. And you see that heat will flow from hot to cool. Okay, so because this is cool here, the water vapor will turn into a liquid, so it's gonna lose energy, so the pressure here will go down. So high pressure, low pressure. Because you have high pressure here and low pressure there, those blades here will start to spin, and then that's how you can produce energy. And then you have a pump, okay, that will push the water up, and the cycle can start again. So each time you are using those convections here, you need to have like a high pressure, low pressure, hot reservoir, low reservoir, a cool reservoir. Okay, so I think now it's clear. Now, can we have the opposite? Yes. So we can have the fluid like uh, gas or any kind of fluid or water or a coolant. We can have it go the opposite way. So from cold to hot, but in that case, you need to put energy in. So work has to be done. So in that case, the hot reservoir will be the inside of the fridge here. So you are taking the warmth from the cold reservoir and dump it outside. Okay. So it means that the fridge will make the inside cooler and the outside hotter. So you have this what is called a cooling coil here, and you have some fluid flowing through this cycle here, and you have a motor somewhere that will push the air from cold to hot. And hot reservoir is outside, the cool reservoir is inside. You also have something called the heat pump. Okay, so heat pump in that case works exactly the same way, except the hot reservoir will be the inside of your house, and the cool reservoir will be the outside, right? So you're taking the heat from outside, even though it's cool, and force it inside. So it's like the reverse process. Okay, so another example could be in the field of earth science. So you see here the upper layer of the earth is broken up into plates, the tectonic plates, and those plates, they can move relative to each other. So you can have subduction here. So you have this layer going underneath this one, or this plate going underneath this one, so you can have volcanoes, earthquakes here. So anyway, this is because of those convection cell that work like a conveyor belt, right? It's moving those plates. So why this happening? Because here it's going to be again hotter. Okay, so it's a hot reservoir. The density will be smaller. So the fluid here, it's not a fluid, it's partially molten, but it's moving very, very slowly because it's not totally molten. And so it's rising, it's cooling, and then it's sinking again. So it's very much like in water. Okay. Interestingly, the heat, you might think the heat comes from the core, which is still hot from the formation of the earth, but most of the heat that will explain why the earth is so dynamic comes from radioactive decay inside here, right? Like uranium, anything radioactive, natural radioactivity that will provide the necessary heat. Okay, so that was a short. And lastly, I want to mention this example that I thought it was cool. It's from your book, and it's used for athletes because they tend to have a very high metabolism and they can overheat. So especially because they have a small surface area relative to their weight, so heat, tend to build up inside. So here they have this interesting device. So here you have a plate, metallic plate here, which is very cool because they have this cool water. It's like a fridge, right? It's like a mini fridge to make sure this is very cool. That plate is very cool. And then here they seal the container. So this is air inside, but they seal it. So here you will have a low pressure inside. So they take some of the air out, right? So here you have low pressure relative to high pressure. So that will draw the blood inside. So that will be the warm blood that is pulled inside here. I mean, through the hand. So it will increase the circulation. Here, the blood will cool down. Okay, so warm to cool. Okay, and the cooler blood go back to the heart, and the heart will distribute the cooler blood everywhere, so it can lower the temperature of the athlete. So if you want here, you can read through. They explain that um, our cooling system works very well around the hands and around the feet. Okay, and you also improve the efficiency of the device by having low pressure here, right? So there is a low pressure, high pressure, so the blood is pushed more efficiently inside the container. Okay, so next time we'll talk about conduction, and there will be some math.